SwayamPrabha. Digital India. Educated India.
Okay, welcome back. In the last lecture, we started a new topic on vapor power cycles, and we realized that Carnot cycle is not efficient if you want to have a working fluid with vaporization and condensation as a part of the cycle. And thus, we introduced basic Rankin cycle. So that was what we considered in the last lecture, where we considered Rankin cycle, where the steam was heated to a superheated condition. Okay, and then we talked about different ways to increase the efficiency of Rankin cycle by using reheat and the importance of high temperature when it enters the boiler. Let's relook at how the Rankin cycle works. So if you look at it, it enters a saturated liquid enters the pump, okay, at 1. The pump increases the pressure of the saturated liquid such that it reaches the boiler pressure, where the boiler provides the heat and it goes up to the superheated condition. And at this condition, it enters the turbine, which isentropically expands to reach a two-phase system, that is at 4. And here it enters the condenser and it condenses so that we obtain saturated liquid. So that means this is nothing but at condenser pressure, this is your boiler pressure. Okay. Now what you should notice here that this part is at low temperature. Okay. So though it's at a constant pressure, but this part is certainly at low temperature, and thus the average temperature is low. And we have discussed this aspect in the last lecture, that if average temperature is low, then the cycle efficiency would be low. So we need to increase the average temperature at which the boiler works, okay, and that's why the reheat was used as one of the solution. So what is the alternative way to increase this particular temperature is to take out some steam from the turbine and mix it in order to increase the temperature, and this is something we call it using a device, okay, and that we are going to call as a regenerator or feed water heater. So what it uses is steam from the turbine, okay. So we will talk about it, we will discuss this process. So one of the key advantage of this is, of course, you are using some part of the heat from the turbine, or using some part of the steam itself in order to increase the steam temperature which enters the boiler. But more importantly also, it helps to prevent a corrosion in the boiler, okay, by removing the air that leaks it at condenser. Okay. So what are the different forms of feed water heater, which is nothing but a basic heat exchanger? You can have a direct mixing, which we call it open feed water heater, or closed mixing or without mixing, or closed feed water heater, which is without mixing. Okay. So let me just first describe this open feed water heater. This is the overall process for, we call it regenerative Rankin cycle, where we are going to use open feed water here. So let's look at the complete process here. So at 5, the steam is at the boiler pressure, it enters the turbine. Okay. So this is 5, this was original point as for without the open feed water. So what we are going to do is, we will take out certain steam at an intermediate pressure, which is 6, okay, and let the rest of the steam expand isentropically, okay. So it goes here until it reaches a two-phase system at condenser pressure, okay. And this 7 condenses and reaches the saturated liquid, and then this particular pump increases the pressure till 2, okay. Now we are going to mix this 6 and 2. So 6 and 2 are at the same pressure, okay. If you look at it, this is at the same pressure. So it mixes and it goes up to 6, that means along this isochore or constant pressure line, it goes up to this point such that this is saturated liquid, okay. So this is your of course saturated liquid at condenser pressure. This is we also can call this as a feed water, okay, and this is as feed water at FWH pressure, okay, and this mixes, and what you get is leaves as a saturated liquid at FWH pressure. So the pressure is now higher at this pressure. So this would be your FWH pressure, okay. And then second pump is used in order to increase the pressure of this fluid from 3 to 4. So that means from this pressure to this boiler pressure, okay. The second pump is used to increase the here where it is now at boiler pressure. Now while doing this, you can also see that the temperature is of 4 is quite high compared to if we have used without the open FWH at 2, okay, and thus the average T is now much higher, okay. So what would be we can analyze this regenerative Rankine cycle with all the energy and mass balance, and we can come up with the work required for pump 1 and 2 and as well as the heat out, okay. And then so we can write down the general expression without going into details of the derivation. As we know that of course the work for this flow system is nothing but V into delta P. This is V1, pump 1 is V1 times P2 minus P1, and for the case of the pump 2, work required is V3 times P4 minus P3, okay. Now we can also evaluate the heat supplied to the boiler, okay. So Q in here is going to be simple the change in enthalpy, that will be your H5 minus H4. What about Q out? So now this Q in is nothing but your per unit mass of working fluid. So here the working fluid, here we can consider this m.5. So if you want to find out the total Q in dot is going to be m5 dot H5 minus H4, okay. Considering Y as m6 by m5, this is the stream extracted at intermediate pressure, okay. So per unit mass of working fluid Q in is nothing but your Q total in, okay, divided by m.5, okay. Similarly we can find Q out at condenser, okay. I can also write this in terms of capital Q in, and Q out is your m dot H7 minus m dot 1 H1, or in other word as m dot 7 is same as m dot 1. And what about m dot 7? M dot 7 here is nothing but 1 minus y times m dot 5 H7 minus H1. So this is a fraction of 5 which goes to 6 and the rest of them goes to the 7th stream. So thus 1 minus y is going to be m7 by m5, okay. So this is your Q out. Thus your Q out as a per unit mass of working fluid is 1 minus y H7 minus H1. And similarly you can also evaluate the work for the turbine out. So that is your T out, okay, and the total work done by the pump, okay. So you can derive this aggressively these expressions, okay. So what we have discussed is open feed water heater. Now we can analyze the closed feed water heater. So the difference between the open feed water is that the stream physically mix with each other, and then you have to operate at same pressure, and that's why the extracted steam from the turbine and as well as the stream from the condenser where the pump is used to bring it to the same pressure in order to mix it. But now for the closed feed water there is no necessity of mixing it physically, and you can have different pressures also. That means the streams can operate at different pressure. So, let us look at how it can be done, and particularly how does it look on a TS diagram. So, the process is the same. So, for example, so you can consider 6, which is your working fluid, and here this, which is your stream, which undergoes some part of it is extracted as 7, okay, and this is at a different pressure. So, you can see this is at pressure, let P dash, okay. Now, the rest of the 8 isentropically expands until it reaches the condenser pressure, okay, and of course, one is at saturated liquid, okay. So, the pump 2 is used to get to this pressure, and this pressure is the same pressure as the boiler now, okay. Note that earlier we had to make sure that the first pump outlet is at the pressure of the extracted intermediate steam, okay. So, you can look at it again, okay. This was exactly the second pump 2 pressure here was same as that of the pressure of the extracted stream, whereas here now you can see that the second stream is at the pressure of the boiler, okay, and the reason is will be very clear, because this pressure need not be same as the pressure at this, which is nothing but your boiler pressure, okay. It is like constant pressure, we want to keep it here. Now, this stream 7 to exchange energy without mixing and undergo a condensation such that your 3 is at saturated, okay, liquid, okay, that means 3 is here. So, while doing so, the 2 at this constant pressure goes to 9, that is 9 is at higher temperature or at the same pressure though, okay. And then this particular liquid, that means your 3 is being pumped such that this is at the same pressure of your feed water, and that means it is pumped here so that it reaches at this on the same isobar, okay, the same pressure, and thus your 4 and 9 are at the same pressure. Now it is being mixed. So, this is your mixing chamber, okay. So, it is being mixed. Of course, the average temperature will be less. So, the final outstream will have lesser temperature than 4, which is your 5. 5 is the stream at this temperature, goes to the boiler, okay. And it should be noted that 4, 9, 5 all have same pressure. So, it is constant pressure mixing, okay, and that is why the 5 is there. So, now you can clearly see that, so this region here is the region which will be supplied by Q. So, this will be your Q in this region, which is the yellow one, okay. So, this will be the region. By using this closed feed water heater, we have also raised the average temperature from what is observed at 2 5, okay, without mixing here, which can exchange heat at different pressure. But of course, also here we are having a physical mixing. So, this is a different way of increasing the heat or temperature of the fluid before entering the boiler, okay, and that is regenerative Rankin cycle, okay. Now, based on this understanding, you can solve the problems by applying the basic mass balance and energy balance here, and this is an example which you can attempt at your leisure, okay. So, with an example with a closed feed water heater. Now, we will try to understand the need for second law analysis for the vapor power cycle. As we have discussed the Carnot cycle is nothing but totally reversible cycle. So, that means there is no irreversibility associated with it. On the other hand, the ideal Rankin cycle is internally reversible, which essentially means there are irreversibility associated outside the system. So, this may involve irreversibilities external to the system, okay, and thus it will be very useful to make use of second law of thermodynamics analysis in order to find the largest irreversibility of the system. So, this is why we may like to use the fundamental understanding of exergy. So, I am trying to now here summarize a simple expression, and in this case for the case of vapor power cycle, we will be making use of a steady flow system, and this is an expression of exergy destruction which is nothing but your T0 multiplied by generation, and that can be written as simply the change in the entropy for the steady flow system, S out minus S in. Now, S out can be written in terms of the contribution due to the mass flow and temperature, heat transfer, and similarly for the in. One can also write this expression in terms of unit mass. So, this is already we have gone through in our earlier lectures. Now, the exergy destruction depends on the, of course, the heat transfer. So, we consider for a cycle. So, this was for a given flow system. Now, if you consider for a cycle, this will be the expression for the cycle, okay, where we are considering the heat transfer for the out and as well as for the in, where the TB is nothing but the temperature at the boundary of the system. For the cycle with only one particular source and a sink, you will have only one term, Q out by TL and Q in by TH. Okay, so assuming this is a sink and this is your source, and this is your, of course, the extreme exergy which we can make use of it. Now, one can do such a problem, analyze it, but the idea behind using of second law is to find out the largest irreversibility, and that is where we can also find out how to improve our process for the problem at hand. Okay? So, by finding out the highest irreversibility, you possibly can come up with a new design which can minimize this such irreversibility. Now, we will talk about cogeneration. Now, in many industries such as that in chemical, pulp and paper and oil production and refinery, you need large amount of energy in terms of input or in terms of heat, and this particular type of energy we call it a process heat. Okay. And these are typically required or typically supplied by steam at 5 to 7 angstrom and 150 to 200 degrees Celsius. Okay. So, what happens is that such a large industry does make use of let us say if a power plant, then it automatically it is generating certain work, okay, and is throwing some part of heat let us say from the condenser. Now, some part of that heat can be used for as an input to other requirements, okay, and this is what we call it as a process heat, okay, where you do not throw all the condenser heat, okay, to environment, but make use of it by transferring to some other process requirement. So, that is why it makes sense to use the already existing work potential to produce power instead of letting it go to waste. Okay. And this kind of combined effort, okay, a plant is called cogeneration plant, okay, where while you produce electricity, okay, you also make use of process heat for certain industrial application. Okay. So, this is an example here. This is a complete process heating plant, a very simple one. The boiler directly heats let us say the steam, and this heat generated is used in some process heater. Okay. So, this QP is nothing but your process heat. Okay. So, let us discuss a bit of that. So, let us say you have a steam turbine plant, and then we are trying to combine this idea, and this is an example of steam turbine cogeneration plant. So, where out of 120 kilowatt which is being used to provide the heat to the boiler, some part of course using turbine is being produced as a work, that is 20 kilowatt, and the rest of them is used as a process heat of 120 kilowatt. Okay. So, this is like a condenser. So, otherwise if you do not use it, it will be wasted. So, now we are trying to use this 100 kilowatt and goes to the other process plant. So, this how do we describe this kind of plant and what is the typical efficiency? In order to make use of this such kind of cogeneration plant, we do not use efficiency, we rather use utilization, because the issue is how to utilize the energies here. So, the term utilization factor is used, where we say the net work output, okay, plus the process heat delivered divided by total heat input, and thus W net plus QP divided by Q in. So, in case of ideal steam turbine, the utilization is 100%, where we are trying to use this to some other part of the plant. Okay. So, we are trying to use this in some part of the plant. Okay. So, thus the utilization factor could be 100, but actual cogeneration plant have around 80% utilization. Now, the problem in this is that it is not very practical, because it cannot adjust to the load. Sometimes you may need process heat, sometimes you do not need, sometimes you want to generate completely turbine work. So you need to have some adjustable load in between. So you can manipulate this, to process heat, okay, depending on the requirement. It's more prudent to have a cogeneration plant with adjustable load. And here, this is an example here. So while from the boiler, some stream is taken out, goes to expansion valve and goes to the process heater, and the rest of them goes to the turbine. And here itself, we make use of 7, which directly goes to condenser, and of course the heat is lost, so this could be waste, okay, and some goes to the process heater, okay. So you can and then of course it goes to the pump, which has different pressures at 8 and 1. Now you can clearly see that how this can be very useful. For example, at very high demand of process heat, okay, you directly pass this completely to your process heater, which means you make this M7 to be 0, okay. In the case of if you make this completely goes, let's say here, which means you don't have any turbine work output, and you pass this stream 4 directly to the process heater, this will lead to the maximum process heating, okay. That means in this such case M5 is equal to M4, no power is produced in this mode. So you can manipulate this now. For example, if you don't need your process heat, then you make this M5 and M6 to be 0, which is your other possibility. And then in that case, the cogeneration plant will work like a simple and ordinary steam power plant. So this is the summary of the energy balance which we can come up with, where of course the Q in is here and Q out is this, okay. QP is your heat through the process heater, and W turbine is of course this, okay. One can come up with this expression completely by doing a simple mass and energy balance. Now of course as we require more efficient plants, it is necessary to come up with a new design, and one of the design is called the combined gas vapor cycle. Okay, and the idea was to make use of a high temperature Brennett cycle, which is your gas turbine cycle, and here you make use of the exhaust of the gas turbine as an energy source to heat up the steam. Okay, so this is the idea of combining your gas vapor cycle, where the gas turbine exhaust is used to heat up the energy. That means instead of having a specific boiler or heat exchanger, you make a use of the exhaust gas as kind of in the heat exchanger. Okay, and this particular way of combining this or combined cycle apparently has more efficiency compared to the individual these two cycle. Okay, and recent gas turbine technology combining with the gas combining with the steam apparently has efficiency more than 60%. Okay, so some of this has become very popular and highly efficient. So this is an example. So this is your gas turbine, that means the Brayton cycle, and this is your simple Rankin cycle. Okay, so clearly instead of a boiler, we are using heat exchanger, where the exhaust gas from the turbine, which is used to heat up the liquid to a supercritical vapor. Okay, so that means from 2 to this is kind of taking heat from the your exhaust gas. Now note that on the TES diagram, this is for the steam, okay, or the vapor, or for water. Okay, so this particular phase diagram is for the water. Okay, and this blue one is basically for the gas. Okay, of course it doesn't have any vapor liquid within this condition, but you have this TS diagram on top of that. It looks like this. Okay, so this is an example of a combined gas vapor cycle, and one can do analysis also of this based on the simple mass and energy balance, as well as one can do a second law analysis for such a process. So let me now end this particular topic. Okay, we have gone through a series of different possible cycles for vapor power cycles, where we started with Rankin, and we talked about the deviation from the ideal cycle. We also looked into different ways to improve its efficiency by lowering the condenser pressure, superheating the steam, increasing the boiling pressure. So we talked about reheat and as well as the regenerative Rankin cycle. And though we haven't done very rigorous analysis of second law, but something which you can do on your own to analyze this second law or exergy analysis of the vapor power cycle. And we also discussed the importance of cogeneration, and finally today's high efficient combined gas vapor power cycle was discussed. Okay, So, that will be the end of the lecture, and we will start a new topic next time. So, we will see you in the next lecture.